Hello to everyone in the room and to those joining virtually over the internet. My name is YJ Mi, and I'm responsible for technology development at TSMC. Today, I'm going to talk about semiconductor innovation for both device and system perspective. Needless to say, these perspectives are probably snapshots of a bigger panorama. I see these as snapshots because the context, the world in which we live, is changing rapidly and radically. When I was in school, there was only one word, the physical world. In the world of the real and the finite, we played with sand and rocks. But not our world today. Today, our world is about fulfilling the promise of seamlessly integrating the virtual and the physical. This world of mixed reality is not static. It changes and reforms as it defines our life in a way none of us can imagine. Today, in our physical world, scientists and engineers, you and me, are already changing how we live, how we get from place to place. The technology behind autonomous driving are fascinating. They include sensors, graphics, and of course, 5G and AI. 5G and soon to come 6G are driving the marvels of AI. And it is the development of 5G and AI and their applications, such as metaverse and autonomous driving, that set the stage for our story. Since the start of 5G deployment in 2019, over 100 mobile operators around the world have launched commercial 5G services, enabling low latency, high data speed, and high device density. The combination of 5G and AI delivers enhanced use cases, leading to new products, applications, and services. It's expected to transform every industry and improving overall quality of our lives. As the growing network of intelligent edge devices bring unprecedented level of convenience for us, high-performance compute become more pervasive at the edge. Gartner expects that by year 2025, 75% of all data processing will happen at the edge, and 5G is the catalyst of this shift. To better understand the new applications and service 5G enables, let us take a deep look at 5G itself. 5G provides 10 to 20 gigabits per second bandwidth with under 1 millisecond latency. With the performance, many applications that were once deemed inefficient or impossible are now within reach. We can download a 4 gigabyte movie in 1.5 seconds, perform robotic surgery remotely, make public utility and agriculture smarter, operate autonomous vehicle that rely on V2X communication for information and safety, and play immersive game with VR goggles. This new application allows us to build a truly networked society. As this device becomes smarter and more connected, we're seeing an explosion in big data. Today, average internet user generates 1.5 gigabytes of data a day. The autonomous car will generate 4 terabytes a day. The smart factory in the future will generate 1 petabyte per day. And video communication service providers, they will each nearly reach the exabyte level. Over a 10-year span, AI computing power demand has increased over 300,000 times. This increases ultimately require advances in semiconductor technologies to provide not just computing power, but energy-efficient computing power. Let's look at 2 innovative products that TSMC customers brought to the market to meet the demand for energy-efficient compute. One example is in high-performance computing, the second in smartphone. In high-performance computing, by combining architecture innovation with 7nm technology, AMD EPYC processor delivers record-breaking energy efficiency for modern data center workloads, doubling the performance or half the power consumption compared to its previous generations. For smartphones, MediaTek adopts 4nm technology for the Dimensity 9000 that delivers 50% better performance, 1.5x download speed, and 25% energy saving than Dimensity 1200, the previous generation built on 6nm technology. The new chip significantly improves responsiveness, connectivity, and ultimately user experience. These massive product-level metrics are enabled by continuous logic technology enhancement that drive performance, power, and area scaling. This chart plots the speed versus area sweep of our ARM CPU core and draw comparisons across our 7nm, 5nm, and 3nm technologies. This PPA improvement enabled the design of faster, smaller, and greener products. Unlike early generations, when Denara scaling principally drove device performance, logic technologies today utilize a variety of materials and device innovations, and it is co-optimized with circuit designs. Here is the first 5nm high-mobility channel FinFET transistors to reach volume production. This fully strained high-mobility channel is provided by a FinFET-compatible process featuring CG as the channel material. The TEM photo on the right shows the same lattice constants. This innovation was built on years of advanced research. In addition to intrinsic scaling, design and technological optimization, what we call DTCO, is a key to achieve consistent PPA scaling. DTCO is enabled by new process technology features such as gate contact over active, single diffusion breaks, fin depopulation, and various self-aligned features. It is also enhanced by well-placed design rule push that improve layout efficiency. Because of DTCO, intrinsic scaling metrics such as gate pitch and metal pitch no longer reflect actual logic density. And what's more, DTCO is not exclusive to logic. SRAM and analog circuits also enjoy PPA benefit from DTCO. These benefits are expected to continue on future nodes. There are also so many advancements and improvements in manufacturing equipment. One of the most important manufacturing gains comes through EUV lithography, which broke the resolution bottleneck of 193 immersion lithography. It delivers higher pattern fidelity, shorter cycle time, and reduced process complexity and defect rates. It took TSMC years of collaborative R&D with ASML before we deployed EUV on our N7 Plus technology. We later extended EUV to more than 10 masking layers on N5 and are continuously increasing EUV usage to drive pitch scaling and density improvement. EUV has a lot of innovative life left in it. We are also actively investigating high-NA EUV, which I'll explain more later. Another focus for technology advances in our industry will be innovative transistor architecture. Transistor architecture has evolved from planar to FinFET and is about to change again to nanosheet. Beyond nanosheet, we see vertically stacked NFET and PFET known as CFET as a likely scaling candidate. Beyond CFET, we have made major breakthroughs in 2D material and 1D carbon nanotube, among others. At the device level, nanosheet transistors offer additional performance and power efficiency. On the left is a TM picture of a nanosheet transistor with tightly spaced sheet to reduce parasitic capacitance. This transistor achieves a smaller substrate swing and better short channel control compared to that of FinFET. It translates directly to lower VDD operation of SRAM, which reduces power consumption and improves energy efficiency. The Shmu plot on the right shows fully functional SRAM at 0.46 volt. Here is an example of CFET inverter scaling. By vertically stacking NFET and PFET, the estimated density gain will fall between 1.5 and 2x after factoring, routing, and process complexity. However, making CFET is by no means trivial. Many new processes and materials need to be invented to realize the promise of CFET. The challenges to stack N and PFET vertically include high aspect ratio edges for gate space and source and drain formation, low-resistant metal gap fill for vertical source and drain connections, high aspect ratio and low-resistant metal gap fill for vertical local interconnect, multiple VT for both NMOS and PMOS, and creating isolations between NMOS and PMOS gate. As transistor channel length and thickness scaling continues, silicon mobility significantly degrades at below 5 nanometer channel thickness, limiting its scaling potential. Emerging 2D and 1D semiconductor can maintain high-quality crystal lattice down to sub-nanometer thickness, and provide good mobility at 3 nanometer and below channel thickness, as shown in the middle. 2D nanosheet and 1D carbon nanotube transistors, shown on the right-hand side, are potential future transistors. Last year, we report our 2D material progress in the journal Nature and at IEDM. We introduced two novel semi-metal materials, bismuth and antimony. Our bismuth contact moly disulfide device achieved a record low contact resistance 5 times better than previous report for the 2D materials, and also a record high on-state current. Antimony is another semi-metal that offers low resistance contact. With a higher melting point than bismuth, it enhances thermal stability while maintaining low contact resistance. As technology scales, contact or mid-of-line resistance become critical for performance. With new low-R materials and the novel interface engineering, we successfully demonstrate 40% low mid-end-of-line resistance. Beyond copper damascene interconnect, we are developing a new metal reactive ion etch process with a novel air gap approach. The air gap shown here can reduce line capacitance by 20 to 30% to improve interconnect performance. We are also investigating a novel 2D interconnect material to mitigate copper interconnect line resistance challenges at small geometries. As the left side of the curve shows, resistivity dramatically increases as copper film thickness goes below electron mean free path. 2D materials, on the other hand, are not sensitive to thickness scaling. Our novel 2D material demonstrates lower resistivity than copper at smaller thickness, potential for further scaling with enhanced performance. As I mentioned earlier, we began leverage EUV scanner and multiple patterning at N7+ to provide aggressive density scaling at each key node. Significant investments, both in manpower and dollars, improve EUV output and reduce defects. We are leveraging the continuous EUV improvement and maturity to deliver technology with the best performance and value. We will develop high-NA EUV scanner, patterning solutions, and infrastructures for future nodes. So far, everything I have talked about has focused on chip-level scaling, but I promise that we'd also focus on system-level scaling. So let's turn our attention to that. And let's start by taking a look back 60-some years. The world's first IC was invented in 1958. It was a collection of a transistor, a capacitor, and 2 resistors mounted on a bar of germanium that is ½ inch wide. 7 years later, a much more sophisticated chip has 3 transistors and 5 resistors on 1.5 square millimeters. Ever since, We have worked to put more and more transistors on monolithic chip. The technology advancement we have discussed so far enable us to do just that. Today, most advanced GPU has over 50 billion transistors on a single chip, creating extraordinary performance and energy efficiency. We are also seeing the rapid rise of heterogeneous integration. That's enabling chip designers to innovate in different domain architectures and create a complete and powerful system to integrate multiple different purpose chips. Integration technologies such as TSMC 3D Fabric pack over 300 billion transistors at system level in a minimal footprint. Today, memory bandwidth deficit is one of the key factors limiting system throughput. For the last 15 years, peak memory bandwidth grew at only 1.6 times every other year, not keeping pace with peak logic throughput that grow at 1.8 times every 2 years. Therefore, unlocking system performance by removing memory bandwidth bottleneck has become a key motivation for advanced system integration technology. TSMC 3D Fabric meets bandwidth demand in various memory integration architectures. Current 3D Fabric offers two platforms: advanced packaging and chip stacking. Advanced packaging is the more mature platform, supporting both homogeneous and heterogeneous integrations. Recently, 3D chip stacking began gain traction, offering a bandwidth advantage of 10 to 100 times higher than 2 and 2.5D, as shown in this picture. At the heart of TSMC's 3D Fabric platform is a comprehensive set of integration technologies to bring multiple chips together with closer physical proximity and higher interconnect density. This integration enables smaller form factor, better electrical performance, and greatly enhanced memory bandwidth. More importantly, this technology allows us to look beyond engineering individual chips and move to integrating them into systems. These chips are so-called chiplets, which has become a very hot topic recently. But some industry pioneers were doing chiplet integration much earlier. Take, for example, our CoWoS technology has been in volume production since 2012. Produced more than 100 products with logic dies integrated with memory chips or another logic die to greatly improve system performance. Systems with several chips packaged together will play an increasingly important role. TSMC InFO integrated fan-out technology has been in mass production since 2016, initially driven by cost-effective mobile application. InFO Pop is the first 3D fan-out wafer-level packaging to integrate SoC with memory package using fine-pitch copper RDLs. In light of cost, form factor, and better signal integrity, InFO technology envelope has extended significantly to allow integration of more functional chips for high-performance computing applications. The platform also features advanced options such as local silicon bridge for finer pitch metal routing and high bandwidth inter-chip communication and high-density decoupling capacitors for superior power delivery. CoWoS, chip on wafer on substrate, technology has been in volume production since 2012. It integrates advanced logic silicon chips with high bandwidth memory to boost system performance for HPC applications. CoWoS features an interposer that horizontally assembles logic and memory chip with fine-pitch interconnect, and advanced options including embedded decoupling capacitors for enhanced power delivery. The rising CoWoS demand reflects the industry's HPC trend. Here is an example of utilizing 7nm technology and CoWoS for high-density HBM integration. NVIDIA delivers equal or better system performance at 1/10 of the cost while reducing power by 20-fold. Vertical stacking provides up to 2 orders magnitude denser connections than 2.5D. TSMC chip stacking offers 2 technologies, microbump and SOIC. Microbump pitch advanced from 40 micron to 25 micron and will continue to shrink. SOIC is suited for chip-to-chip integration with more stringent pitch requirement. SOIC bump pitch starts at 9 micron and is moving to 6 micron and beyond. One of our HPC customers, AMD, achieved significant performance improvement when it implemented TSMC SOIC chip-on-wafer technology to stack SRAM on logic in its latest data center CPU, EPYC. The EPYC processor is a living proof of the importance of 3D IC technologies in unleashing system-level innovation. 3D chip stacking can be further integrated into 2D and 2.5D packages to deliver the ultimate system integration solutions. Complexity of design increased exponentially from 2D to 2.5D and 3D integrations. And the tightly coupled brand new chips and package code design flows become a must for faster design convergence. Many new aspects has to be considered in these new design solutions, including thermal-aware design to properly distribute heat dissipation, known-good die, known-good system, known-good package testing, die-to-die IOs, ESD solutions, signal and power integrity, static timing analysis, and design for test, and new power distribution network design. TSMC is working with OIP ecosystem partners to provide a tightly coupled chip and package co-design flow for our customers. Designing and integrating 3D chips for system innovation creates a new set of challenges. One of the key SOIC design challenges is to partition an SoC into chiplets. After partition, we need to design die-to-die interfaces, conduct multi-die system analysis, and optimize thermal performance to achieve system-level optimization. TSMC 3D Fabric design platform provides effective solutions to speed up chip stacking and package design. Today, I'll focus on 3 key activities: modularization of the design flow, hierarchical timing analysis to solve the corner explosion problem, and hierarchical thermal analysis to balance runtime and accuracy. For multi-die static timing analysis, the complexity grows exponentially compared to a single die analysis. Comparing a 6-corner analysis for single die, 2-die stacking will require 72 corners. EDA analysis runtime will also increase by 12 times. With the innovative die-to-die interface timing model and hierarchical timing analysis, the runtime can be significantly reduced from 12 times to only 2 times. Thermal is another important 3D IC design consideration. Fast yet accurate thermal analysis is important for early design exploration. However, high analysis accuracy usually comes with very high computation cost. This requires a methodology innovation. Collaborating with our EDA partners, we solve this problem through a divide and conquer approach. We first identify hotspot through the conventional coarse grid approach. Then the hotspot is modeled in detail, and we apply a more expensive thermal solver. As shown on the right-hand side, this go-hierarchical methodology enables us to predict maximum hotspot temperatures with the required accuracy while reduce runtime by 10x. As more and more 3D IC package technology are developed to meet various application needs, the number of design elements and their combination also quickly grows. To cope with this challenge, TSMC has classified key building blocks of all 2D, 2.5D, and 3D packages, including a bump module, a via module, capacitors module, interposer module, and die module. Based on these modularized components, TSMC has created the 3D blocks modularization standard and worked with EDA partners to build highly streamlined design flows. We believe designers will see a tremendous boost in design productivity from these new flows. 3D IC ushers a new era of system integration, where more transistors, more memories, and more chiplets are integrated and optimized to enable an energy-efficient compute at an unprecedented scale. Transistor technology progressed from 2D to 2D with DTCO, then to 3D. More memory can be achieved while vertical stack SRAM or on-die emerging memory, such as MRAM. System-level integration spans from 2D to 2.5D and into 3D. And end-to-end optimization encompasses technology, device and circuit, architecture to system and software, added by switching energy reduction and thermal management. It's going to be our collective challenges to figure out how to innovate so that we could harness the benefit of these truly exciting technologies. When I look into the future, I see the vast varieties of opportunities for innovation at system and product level. Innovations that will help the visionaries transform every industry: healthcare, automotive, finance, retail, just to name a few. We can also be assured that whenever there is a vision, the technology community will find a way to achieve that vision. And I'm very confident that you all will play a part in getting us there. Thank you very much.